All right. So our next speaker is Professor Matthew Madaherchervel. I still ruined your name.
That's pretty good. Madaherchervel, thanks.
Yes, from Perimeter. And it continues on with the discussion of FRBs, but talking about combining them with a kinetic Sanyaev-Zeldovich effect. So go ahead, and I'll give you a warning with 5 minutes left if that's what you need.
Thanks a lot. Thank you for the opportunity to talk about this. It's very nice to follow Pawan's really nice talk on potential cosmological applications of FRBs. We just heard about how fast radio bursts can be thought of acting as kind of like a backlight to probe the intervening plasma, the cosmological distribution of plasma. And I want to kind of connect that to a probe in the CMB that I'm pretty excited about, which is the kinetic Sanyaev-Zeldovich effect. And I'll show how we can do cosmology when we combine these two different probes. Because the kSZ is usually thought of as something that's used to probe astrophysics and not really cosmology. And I'll show that connection and why that limitation comes about and how we can overcome that using FRBs. There's several moving parts to this talk, pun not intended. So I'll just try to give you kind of a general framing for what the picture here is. So we're all familiar with the idea that the cosmic microwave background is a snapshot of the universe. At the point of recombination, up to that point, the universe is completely ionized, and then hydrogen recombined, and we had a neutral universe until stars started forming, and an energetic phenomenon in the universe started ionizing the universe again, reionized the universe. And now we live in a universe that's primarily consists of things that are practically fully ionized. And so there's been this, many new ways of looking at the CMB beyond just thinking of it as a snapshot of the primordial fluctuation, to thinking about the CMB as a backlight that has tiny anisotropies on it imprinted from things like gravitational lensing, but also scattering of the CMB light off of these regions of ionized gas in the universe, ionized plasma. So that's one backlight that we're going to be thinking about here in the next 30 minutes. The other backlight that we just heard about is fast radio bursts, right? So in this talk, now we're going to think about whatever they are, whatever is causing these, highly energetic processes potentially at higher redshifts. We can think of using them as another backlight, and then combining the two will allow us to break some degeneracies. Okay, so there's lots of free electrons, and because the universe, because it's gravity, things are moving, so there's motion in the universe, and that leads to this effect called the kinetic SC effect. So the background CMB, these photons, when they encounter regions of the universe where there's ionized electrons with bulk velocity, that leads to an additional Doppler shift of these CMB photons when they scatter off these electrons. And so beyond the primordial fluctuations, what you get are additional anisotropies that are much smaller than the primary CMB fluctuations. And these anisotropies, due to the kSZ effect, they cause the CMB to be colder in regions where free electrons are moving away from us, and hotter in regions where free electrons are moving towards us. And so it's kind of a dual probe of two things. And that's where this fundamental degeneracy comes from. It's a probe of the radial velocities in the universe. So it requires motion of these free electrons, but it's also a probe of the underlying free electron distribution of the overdensity of underlying electrons. And in some sense, you want to think about the radial velocity part as the thing that contains the cosmological info. And you'll see in a bit why this is interesting. And then the astrophysical part is really this uncertain astrophysical part is the overdensity of electrons. And for this talk, Pawan mentioned that you can think about both the reionization epoch, but also what I'm particularly interested in this talk is just the ionized gas and in between clusters at low redshifts, where you have clusters of galaxies and stuff in between clusters. So that's what I'm thinking about when I'm writing down these overdensities of electrons over here. It's the ionized gas in between clusters between redshift 0 and 6. So just to give you a visual picture of what that looks like, If you zoomed into the primary CMB, just the primary CMB without any of the foregrounds, without any of the additional effects, then you see these familiar fluctuations in the CMB. That it's a snapshot of the radiation at redshift of 1100, and those fluctuations are the level of something like 300 microkelvin, right? So it's 1 in 10 to the 5, 1 part in 10 to the 5 fluctuations, tiny fluctuations, but even much tinier than that are these additional anisotropies. So this is a snapshot of the what the kSZ effect, the kinetic SC effect due to moving clouds of ionized electrons looks like in simulations. And you can see that you have this picture of how these fluctuations really kind of trace halos. And they're redder in regions where the radial velocity field in the universe. And that's a large scale field that's modulating this. So in these regions, the radial velocity is pushing things towards us. And in the bluer regions, radial velocities are moving away from us. And so that's kind of how it shows up in the observed CMB at the few microkelvin level. It's a tiny signal. But if you plot it in a certain other way, if you look at ask the question, what is the power spectrum of the CMB and its different components, the black body components of the CMB is a function of scale. As you go to smaller scales on the right here, the familiar acoustic oscillations of the primary CMB up here in blue, in the orange, which includes the gravitational lensing effect. But once you get to small scales, and these are the scales that are really going to be probed by these high resolution ground-based experiments that are really just ramping up right now, like an advanced Atacama cosmology telescope, the South Pole telescope, we're going to be measuring these small scales much better than the Planck satellite did. And so what that really means is that there's this uncharted territory of the kSZ effect, which dominates above all the other black body signals in the CMB. And so far, the effect has been detected in many different ways. But by different experimental groups, but only at something like the 10 sigma level. But this is expected to improve really quickly once you have deeper CMB observations, higher resolution CMB observations, and lots of overlap with galaxies. As we'll see, this is a signal that you find through cross correlation with the positions of galaxies. So if you have more volume of the universe that you're probing, and what we're forecasting is that you're going to be, making percent level or sub-percent level measurements of the kSZ effect. So what could we potentially learn with this effect? So we're going to get to FRBs eventually because of this astrophysics cosmology divide, essentially, right? So if you knew the astrophysics part, if you knew the distribution, the optical depth of galaxy clusters, if you knew that, if you fixed that, then in principle you could do lots of cosmology with the radial velocities, as we'll just talk about in a bit. But if you assume that you knew the cosmology and you pinned it down, let's say from Planck's primary CMB experiments, and what the kSZ effect is traditionally thought of as measuring really interesting questions. If you're looking at the kSZ effect from reionization, then you're studying the reionization epoch. The more recent epochs kind of probe the questions like where baryons are. And so if you try to make a census of all the baryons, you find that a large chunk of it is just not visible. And now we think that we might have found these baryons in the warm, hot intergalactic medium through these SC effects. And you can ask questions about things like halo energetics and baryon feedback by understanding the astrophysics. But the important thing here is that these two are degenerate. If they weren't, if you could isolate just the radial velocity part, then the reason this is really interesting is because just from simple continuity equation on the largest scales of the universe, if you're measuring the largest scale of velocities, then what you're really measuring are the unbiased density modes in the universe, right? So because you're just relating the velocity field to the underlying density field, the matter over density, the total matter density. And the continuity equation in Fourier space just tells you that this is related through the growth rate f, which is the logarithmic derivative of the growth factor, and a factor of k, right? So that's where the cosmology is coming from. You can either think of it as probing the underlying density field, which in itself is interesting because that's a total matter field, including all of the dark matter, or the growth rate itself, which is affected by things like the presence of massive neutrinos, the dark energy, changes to the dark energy equation of state, modifications of gravity, etc. Right? So this is why, if you could pin down this optical depth degeneracy, right? If you could pin down the astrophysics, then the velocities that are probed by the kSZ effect are this amazing treasure trove of information. again, this is just reiterating the idea that, you know, if you, traditionally you can't do this because the astrophysics is complicated. People call this the cluster optical depth. It's just the fact that you don't know the optical depth of the galaxy clusters, but includes the uncertainties in the shape of the electron profile, the distribution of electrons. We know that, you know, the distribution of electrons doesn't necessarily need to trace the dark matter. It can have a different shape because of baryonic feedback. All of these things are highly uncertain. And if you try to forecast how well you can constrain the growth rate, the relative uncertainty of the growth rate as a function of redshift, then you just become limited by the prior you have on the optical depth, right? So that's the limiting thing. So in a series of papers, we set out to try and understand this a little bit more systematically in the hope of like identifying potential ways to work around this. To set that up, let me just give you a kind of cartoon picture of how the kSZ works. I previously showed you how the kSZ looks like in simulations. But a nice way of thinking about the kSZ effect is just as a modulation of the power spectrum that you see in the CMB, but not just the power spectrum of the CMB itself, but the cross power spectrum of the CMB with the positions of galaxies. If you simply try to cross correlate the CMB temperature with the positions of galaxies, then on average, things are as likely to move away from you as they are to move towards you. And so you get a 2-point cross correlation that's 0. But what you want to think of is in regions where things are moving towards you, it's a positive cross correlation. Things where things are moving away from me, it's a negative cross correlation. And so there's a modulating field. The velocity itself modulates this cross power spectrum between galaxies and the CMB temperature itself. And so you know, once you sum up over all the modes in the universe, then it ends up looking like this. But what that essentially motivates is a quadratic estimator. So instead of looking at the diagonal cross power between the overdensity of galaxies as measured using a galaxy survey and the CMB temperature on small scales, what you want to do is sum over quadratic pairs of modes. And just a few lines of just schematic math here show that if you plug in what the anisotropy of the CMB looks like, the temperature anisotropies in the CMB looks like, which is an integrated line of sight projection of the product of the overdensity of electrons and the velocity field itself. The Ks here stands for the small scale wave numbers, right? So you're summing over pairs of products of small scale modes in the CMB and the galaxy overdensity. But that cross power spectrum is modulated by the long wavelength velocity modes. And so those long wavelength modes don't matter in this integral. And you just pull it out of the integral, and what you end up getting is a reconstruction, once you've summed over these pairs of modes, that's proportional to the underlying cosmological velocity modes on the largest scales. But that entire thing ends up being biased by an uncertain factor, which is an integral over the small scale modes. But what it ends up precisely being is this cross correlation between the galaxies and electrons. So that's what we're showing here, is we're kind of clarifying what the optical depth degeneracy really means. What that means is that you can use kSZ to reconstruct the largest scales in the velocity of the universe, but you can't know its amplitude. The amplitude of that entire velocity reconstruction is completely uncertain. It's a scale independent number, and I'm going to call that BV for the rest of the talk. It's the bias to the velocity. So if you combine a galaxy survey and a CMB survey, you can get some cosmological information from it, but it's a scale dependent part of the cosmic velocity field. The overall amplitude or normalization of that velocity field is completely uncertain. So after velocity reconstruction with kSZ, what you end up having is a probe of the underlying density modes multiplied by the growth rate, uncertain by an overall astrophysical factor, the velocity bias or the optical depth. And you have the galaxy density itself. And an interesting thing that comes out of this is that if you try and convert the measurement of the velocity modes to an underlying measurement of the density modes, and you compare with how you can do that if you did a similar conversion of the underlying density modes from the galaxy modes itself, then the underlying matter density looks like this curve. So this is the familiar, PFK, the power spectrum of matter. And that's measured with some short noise from a galaxy survey. But if you look at what the reconstruction noise that you get from the CMB inferred cosmic velocity reconstruction is, then that because of this 1/k factor in the velocities, in the way the velocities relate to the underlying density modes, this beautiful fact comes out of it that if you use kSZ to reconstruct the underlying cosmic velocity modes, then you're really getting a reconstruction of the largest scales in the universe with a noise that's much lower than what you could have, what you would have seen if you just used the galaxy survey alone. So the simple combination of the CMB survey with the galaxy survey allows you to reconstruct these larger scale modes with much higher fidelity. Okay, so the recap here at the 15-minute mark is that by using this kSZ probe, by combining a galaxy survey with a CMB survey, you have a handle on the largest scale density modes. Okay, that's interesting for cosmology. The problem is that the overall normalization of that field is unknown. It's a scale independent normalization that people have traditionally called the optical depth that depends on this uncertain astrophysical quantity, which is the cross correlation of galaxies and electrons. However, you get this with much lower noise in galaxy surveys. And an application of this, which I'm not going to spend time on because that's not the main point of this talk, is that because this uncertainty is a scale independent normalization, what that means is that you can use this to constrain scale dependent physics on the larger scales. And one example of this is the scale dependent bias due to local primordial non-Gaussianity. And so this is one of the applications that we explored in one of the papers in the series, which showed that kSZ ends up being actually an amazing probe of local primordial non-Gaussianity that improves existing measurements if you just use a galaxy survey alone by factors of 2 to 3, allowing you to probe multi-field inflation, right? So that's what you can do despite having this astrophysical uncertainty from the optical depth or the unknown PGE on small scales, which you don't know, right? So you can marginalize over that fully, but since it's just an amplitude uncertainty and you're looking for a scale dependent effect, you constrain FNL really well. But what if you were interested in the actual amplitude of the velocity field itself, right? So what do you need to do if you wanted to constrain the amplitude of the velocity field, which is proportional to the growth rate in the universe? And so this amplitude of the amplitude of the growth rate, which comes out as a normalization of the which comes out as just something that multiplies the underlying density modes when you look at the velocity reconstruction. That's going to be affected, as I said earlier, by things like the sum of neutrino masses, the dark energy equation state, modified gravity. If you're marginalizing over this uncertain astrophysical optical depth, then you completely lose constraining power on the optical on the amplitude of the growth rate, right? So that's the sad part of this, right? So breaking this degeneracy, the fact that the BV and the F multiply each other, breaking that degeneracy requires an external measurement of the cross correlation of galaxies and electrons. Okay, so that's the only way you can do this. That's the only way you can use kSZ if you're interested in measuring the amplitude of the growth rate. As I already just mentioned, it's a separate talk. And if you're looking for scale dependent effects like FNL, then you can do this even while marginalizing over the optical depth. If you want to measure the amplitude, you need to measure PGE, right? So what is a way of probing the free electron density? And now this is hopefully connecting to the FRB section of this workshop, right? Is that we've just heard from Pavan, right? That you can probe the free electron density field in the universe by looking at the dispersion measures of fast radio bursts. So this is what we explored in a paper, but just to recap what Pavan already mentioned. When you see a fast radio burst, you see a time lag in the arrival of the pulse based on its frequency, just because of dispersion. The electromagnetic waves as it interacts with the intervening plasma, the higher frequencies push past. That dispersion measure for each fast radio burst is measured by radio surveys with very small error, right? So every fast radio burst you measure, you get a really good measurement of the dispersion measure. And there's potentially a really large number of these energetic sources at cosmological distances, as we just heard about. The dispersion measures are actually really large. You can't just explain that just with just the contribution from our own Milky Way. Some part of it might be from the host galaxy, but we've also seen that follow-ups of some FRBs showed there are cosmological redshifts. And so the CHIME experiment, as you'll hear from Kendrick's talk coming up next, is seeing lots of these. And so we really want to ask, can we use the fact that the dispersion measures are actually probing the integrated line of sight density of free electrons to break this degeneracy? That's what we explored in a paper. But just to set this up, there's a very nice paper from Matthew McQuinn in 2013 that kind of looks at the first step of this question, like what does it? What is if you had a map of FRB dispersion measures, then what the anisotropies in that map are really coming from the fact that you're, so there's the first part is showing the number of times you intersect a halos at above a certain mass. As you look through the line of sight and you see a certain dispersion measure. And the bottom panel here shows the mean dispersion measure as a function of redshift. And so as the higher redshifts you go to, the more stuff you're looking through. And the dashed lines here show the scatter in the dispersion measure itself due to the fact that you're hitting different halos as you go along the line of sight. And so you can compare simulations or halo models, and they show you that there's a certain amount of scatter in the dispersion measure that you expect as you go to higher redshifts. And so the essential idea is that the dispersion measure that you measure has these contributions not just from the source or the host of the FRB itself and the Milky Way, but the intervening plasma. They're really interested in the anisotropies in that dispersion measure due to the free electrons in and around halos. So this is essentially probing the distribution of free electrons that constitute a large chunk of the missing baryons that people are worried about. The essential idea that we're putting forth in this paper is that if you're trying to measure the growth rate, the amplitude of the growth rate, using the kSZ reconstruction, whose amplitude you're uncertain about, so you're using a certain sample of galaxies, right, to cross-correlate with the CMB, and you don't know the electron distribution in those galaxies a priori, right? So it's an astrophysically uncertain quantity. So what you want to do then is take a bunch of FRBs that are behind those galaxies, and then you want to look at you want to make a map of the dispersion measures behind those galaxies and cross-correlate that map with the same sample of galaxies whose PGE, the cross-correlation of galaxies and electrons, is the uncertain quantity that's limiting your ability to constrain kSZ. If you do that cross-correlation, then you measure precisely the quantity, the power spectrum that you were uncertain to begin with, right? So this weighted integral of the PGE, you can translate that to a measurement with error bars if you were cross-correlating FRBs with a galaxy sample like DASI. So that's the essential idea. You can translate this to a prior on the optical depth that you can obtain. The more FRBs that you have, the lower the noise in the map of dispersion measures that you make, and the better you measure, the lower smaller the error bars on the underlying galaxy electron crossbar spectrum. And so what you can now do is you can take the velocity measurements whose amplitudes are uncertain, and you can break that optical depth degeneracy. You can add a prior. So now I'm looking at the constraints on the growth rate. So the product of the growth rate and the amplitude of matter fluctuations, F sigma 8, as a function of FRBs. If you didn't have any FRBs, then I'm completely marginalizing over the optical depth. The optical depth is a weighted integral of the galaxy electron power spectrum. Then you have no constraining power on the left here, if you have no FRBs. As you add more FRBs, you're getting more and more, a tighter prior on the optical depth, and you get a better, much better constraint on the cosmological F sigma 8 until you saturate that just because of sample variance, right? So the sample variance in the underlying electron density field itself, if you have enough FRBs, you're not going to improve over that. But what you're seeing here is that even with a catalog of something like 1,000 to 10,000 FRBs, depending on the intrinsic scatter of the dispersion measures itself, which is currently an uncertain quantity.
Matt,
To be
5 minutes.
Yeah, thank you. So this is an uncertain quantity that we're varying in our forecast here. The scatter and the dispersion measure, which is contributions from just, for example, the intrinsic variation of the host contribution to the dispersion measure itself, which we have really no idea about, but also residuals in our modeling of the Milky Way dispersion measure. So depending on that, you can get percent level to 10% level constraints in F sigma 8, potentially better than percent level constraints on F sigma 8, which is really making this kind of a competitive probe of cosmology, right? So you're measuring the growth rate in a way that compares to other measurements like things like redshift space distortions, or RST from galaxy surveys. So that's the essential idea, and just like a couple of minutes on the outlook here, you really need more than 1,000 FRBs to do interesting science. The exact number depends on the scatter of the DMs, which you still don't have information on. You do need to get some information on the redshift distribution of the FRBs itself. You need to know, for example, that they're behind the sample. If they're behind the sample of galaxies, then that's pretty much all you need to know. But in practice, you're going to have some overlap. And what that means is that you need either localization capabilities in radio instruments. You might hear more about that from Kendrick, or you can use statistical cross correlations with galaxies to kind of constrain the redshift distribution of the FRBs itself. The clustering of the sources itself can affect the dispersion measure cross galaxy cross correlation, but it's likely negligible. There's a recent paper by David Alonso that looks into this a little bit. But I think I'm pretty optimistic about the outlook here. Future experiments could potentially measure tens to hundreds of FRBs per day, and that's we're really talking about being this regime of like hundreds of thousands to a million FRB catalogs over maybe 10 years, which allow you to really take the kSZ measurements and transform it into a powerful cosmological probe. So I'll just leave the conclusion slide here. So traditionally there's the optical depth degeneracy, the cross correlation of galaxies and the free electron distribution that has limited our ability to do cosmology with the kSZ effect, except if you're looking for scale dependent effects. If you're looking for scale dependent effects, the astrophysics doesn't matter. You should read the paper by Maritz Manschmeyer, myself, and others to see how things like FNL can be really improved by this. But if you're interested in the scale independent amplitude of the growth rate, and one potential way to break this degeneracy is to get measurements, to make maps of FRB dispersion measures and cross correlate that with the same sample of galaxies that you're using for the kSZ measurement. Thank you.
Okay, Matt, thank you very much. And not only that, you were slightly ahead of time, which is impressive. So we have some questions. And the first one with his hand up is Pawan. So go ahead, Pawan.
Okay, thank you. Matt, thank you for a very interesting talk. I have a quick question, and that is that you are using your method that you suggested is using FRBs to get tau, the optical depth, to get the velocity field. Now, the tau you get from DM is not only coming from electrons in the vicinity of the galaxy, but it's coming, it's the whole entire column, which means that there is a lot of contribution to the tau that is coming from the IGM, right? Between the FRB and the host and the galaxy that you have in the foreground, and then also electrons between the galaxy and us. Mm-hmm. So that is to say that you are kind of getting a tau, which is more than the tau associated with the electrons moving with velocity that you are trying to determine. And I'm sure you have thought this thing through to see
Yeah, so the statistic that we're using is not just the dispersion measure that we're seeing, but it's the cross correlation of the dispersion measure with the sample of galaxies whose star we're interested in. So, for example, just to take the Milky Way as an example, if you didn't subtract the Milky Way contribution, then that's not going to cross correlate with the map of galaxies. It's just going to add noise, right? So you wouldn't bias your measurement due to other things in the way. You just add noise from the other things in the way. So it's the cross correlation that's specifically being used to constrain the optical depth. The optical depth, not the full optical depth, but the optical depth that's relevant to that galaxy sample that you're interested in. Does that make sense?
Right. Maybe we should talk offline.
Yeah. So the basic idea is in the cross correlation, anything that's not correlated with the galaxies itself is going to just it's just going to cancel. It's just going to add noise.
Okay.
Yeah, I'm happy to talk about that more offline.
Okay, Norma also has her hand up. Norma?
Yes, thanks. There is a very interesting cosmology which can be extracted from Zunayev, Seldovich, as you showed, and several other information. Restricting to what you present, as conclusions, I would like to point out, even if it becomes some popular these times, about Zunayev, Seldovich, and large-scale structure observations, the fact to measure or place some constraints in FNL, primordial non-Gaussianity, and then touching inflation models. I should say that the FNL, as you know, from CMB, is smaller than kSZ. So the limit about 5 is not for testing, but I should say for excluding a multi-field inflation or inflation with multi-fields, because it's known that produce isocurvature fluctuations in an amount which are already, dismissed by the CMB observation. So in most of the model, otherwise you need to start to tailor it, to make tailored parameters. And so still, it is interesting. You could reach this FNL about 5. I can advance from now on that could be interesting, and then to not to test, but put more excluding about excluding a statement about multi-field inflation.
Yeah, I agree. there's getting to FNL of around 1 is interesting. There might be wiggle room around it if you want to say that you haven't ruled out interesting models, but that's precisely the goal of the method that I hinted at. As you mentioned, current constraints from the CMB put FNL around 5. If you're just using a galaxy survey, then you get FNL of around 2. But combining with the kSZ, you're improving it to the point where you're really probing regions of parameter space in certain models that predict.
Yeah, I should be. Thank you. I should be more precise. If you this picture, which between FNL 0 and FNL 5 set, there is the interesting place for FNL about 10 minus 2, which is what is pointed out for all observations, CMB plus large-scale structure combined. Via what is called the precision set cosmology. So this is the. This is the figure 10 minus 2 in agreement with all other set of parameters for inflation models or primordial, and it could be, in any case, it could be great to reach some
Let's postpone this to the discussion section.
Thanks.
Thanks for that.
A lot, because Francesca wanted to get presumably a question about this particular
Yeah,
talk.
sure. A quick question. So I wonder about the use of fast radio burst as standard candles in this method. So what if fast radio bursts have an emission process that evolves through cosmological times? I mean, is this can you modify this method to include this, or what would this be problematic?
That's I think I'm not familiar with attempts to use them as standard candles, but I think it wouldn't end up mattering, right? So the properties of the host really don't end up mattering. They just so you're thinking of like things that happen with the intrinsic dispersion measure due to the host itself. The idea here is really, again, just like to cross correlate with the sample of galaxies, and you just pick out the electron density along the way that's correlated with the galaxies itself. So if there's variations in the host, if I'm understanding your question correctly, it shouldn't affect this method.
I was thinking about, for instance, if the emission is different in terms of absolute luminosity.
Yeah, so here you don't use the information about the luminosity itself.
Okay.
You just use the dispersion measure, right? So you're basically throwing out any other information about the FRB other than just the slope of the time lag versus the frequency. But there might be other uses of the luminosity information itself. That's an interesting thing that I haven't thought about.
Thank you.
Okay, were there any more questions specific to this talk? I'm trying to preserve our schedule so that we have a long time for discussion afterwards for the more general aspect. Are there any more questions? If not, we'll thank Matt and we'll move on to our next